This is probably going to be a different talk than what we have seen so far. It's most of the talks which you've seen, and there have been a lot of wonderful talks here over the last 2 days, have been mostly about what you can do for RISC-V. Here I'm going to bring a different perspective. I'm coming from a Gen Z perspective, and I would like to ask you what you can do for the Gen Z. That is, what RISC-V can do for Gen Z. So what I'll do is I'll first give you a motivation for the Gen Z fabric interconnect, and then talk about what I see as areas where RISC-V could make changes either in the ISA or in their systems to be able to support a Gen Z fabric. So the main reason for or the motivation for a Gen Z fabric is that the compute memory balance is degrading. We have seen over the last 10 years that Moore's law has kind of started to decline. It's no longer relevant. We have seen that Dennard scaling has also gone out of fashion. And we are seeing that to solve that problem, what the processor vendors are doing is that they are creating these huge monsters of CPUs with lots of cores on them. And if you can see in the 2019 timeframe, you'll probably see around 64 plus cores. This is from the x86 perspective, which I'm talking about. But you will probably see that even with other processor vendors. So you'll see around 64 plus cores. And the thing to note is this part. There are around 4,000 pins which are going to be there on the processor. That's really huge. That's a lot of real estate which is being taken up by pins. Either it's the DDR4 pins, or it's the memory, or it's the PCIe-related pins. And in 2019, you also see that there'll be around 8 DDR channels which will be there on the system. There'll be around 64 PCIe lanes. So it's a huge processor which is going to be there in that time frame. But even though we have gone to this multi-core architecture, I think the challenge remains that we are not able to feed these cores fast enough. We are not able to feed the cores either with the I/O or with the memory fast enough. And that's the huge challenge which Gen Z is trying to address. So to again reiterate that point, you will see that the memory and I/O bandwidth capacity per core has been steadily on the decline. So even though we've been increasing the number of cores, we see that the bandwidths are decreasing over the last 10 years pretty substantially. We did get a small bump with the 6 DDR channels in 2017, but it continues to go down after that. The other motivation is, what you would have seen is that memory and storage are kind of converging finally. And we had this huge difference between the memory and the storage latencies, and that got addressed to a certain extent with flash. And now we are seeing it addressed even more with things like SCM, which is the storage class memory. Hewlett-Packard Enterprise was one of the first in this space with Memristor. But now you see technologies like 3D Xpoint from Intel and Micron, which are hitting the market. So once you have this storage class memory or the persistent memory getting into the system, you will need to have memory semantic operations, or where the CPU has to talk the language, or the memory has to be able to handle the language of the CPU. And the CPU is primarily doing load stores. So you want to be able to handle those load stores in the technology. So what's the solution? The solution for this is, one of the solutions for this is a fabric interconnect technology called Gen Z. And its main characteristics, you can see on the right side how a Gen Z fabric would look like. So it can either be a point-to-point or a switch-based. Any topology would work with Gen Z. And you can attach almost anything into the Gen Z fabric. You can attach an SoC, like a RISC-V SoC, or an FPGA. You could attach GPUs. You could attach DRAM, SCM, or almost anything. So it becomes like a universal fabric, and it democratizes the whole fabric in terms of the protocol overheads. So what does it provide in terms of key features? If you see on the top, the performance is very high with Gen Z. You can go from 16 giga transactions per second signaling to 112 giga transactions per second, which is defined in the spec, and you would see that probably with PAM4 kind of signaling. Very low latency, and if you see that in terms of bandwidth, it can go up from 32 gigabytes per second to 400 plus gigabytes per second per memory module. It's a very reliable interconnect. You can almost flatten the memory and storage hierarchy, and you can have huge memory or a fabric-attached memory which can be supported with Gen Z. The other thing is, it is a very reliable protocol in terms of having this multiple levels of paths which are enabled in the fabric, and so you will not have any stranded resources or single point of failure. So you could always have a different path to which you could take to the device. Again, similar to the RISC-V vision, the vision for Gen Z is that it has to be highly secure. And so it will provide strong hardware-enforced isolation and security. And you will see later that this is one of the areas where RISC-V could do a lot to work along with Gen Z and make the whole system and the fabric secure. It's very flexible. It provides multiple topologies, component types, etc., which we've already talked about. It will also support new form factors in which you can put these SCMs or the DRAMs and things like that. And multiple media types can be physically co-located. So you could have a DRAM or an SCM on the same module. And again, like I said, it scales from a single motherboard. So you could have Gen Z within the motherboard, or you could have it in the fabric itself as a rack scale kind of interconnect. One thing which we are doing with Gen Z is to make sure that it's compatible with what we have today out in terms of systems and operating systems. So we want to ensure that it is compatible. And so you can have a system which is running PCIe today, for instance, be able to discover a Gen Z fabric. It's futuristic. So it's going to break the processor memory interlock, which we have seen. And I'll show you that, demonstrate that on the next slide. And it will, from the ground up, it will allow you to support the persistent memory semantics, which we are going to see a lot more in the future with SCM. This slide basically shows you an example of how Gen Z can help us. So on the left-hand side, you see an SoC with a memory controller. And you have this CPU, which is talking to the memory through the memory controller. And so the traditional memory bus has this media-specific logic integrated into the SoC. It's a tight coupling, so every time you have a new protocol which comes like a DDR3 or a DDR4 or a DDR5, you have this interlock which gets created. And so you have to have new systems which come out every time you have to support the newer technology. What Gen Z does is that it moves this logic of actually what talks to the media to the device itself. So it creates a level of abstraction. And so you have the Gen Z logic sitting on the SoC or the CPU side, and then it talks to the Gen Z logic on the media controller side. And what this does is that basically the CPU now talks only the language it knows, which is load stores. And the Gen Z logic in the CPU will take care of translating that to, the Gen Z logic on the SoC side will transport that over to the memory module, and the logic there will take care of the actual media specifics and be able to do whatever it needs to do. And so this, as I said, it breaks the interlock. So you can see on the right-hand side, you have you can see that you can now have different SoCs and memory types which can be supported, and you have backward compatibility, which is there even when you introduce a new module type. This slide basically will give you an idea of the kinds of bandwidth which you can expect with Gen Z. You will not see Gen Z being the only interconnect in systems in the near future. We are hoping that we will have Gen Z supported along with DDR probably in the initial time frame. And you can see that if you have a mix of Gen Z and DDR, you can actually go up to really huge aggregate memory application bandwidth. And like I showed on a previous slide, with the advent of things like HBM, you're seeing really huge terabytes per second of bandwidth which are there, which goes to the HBM, and that doesn't really match up with the kind of bandwidth which we have going from the CPU to the memory or the CPU to I/O. So you need to be able to bridge that with something like Gen Z, which can take you to the levels of bandwidth which are required for these new architectures. And you can see that with 112 gigatransactions per second, you can go to 1.4 terabytes per second with Gen Z. This slide basically shows you the key features for Gen Z, and the idea here is that you will probably see RISC-V adopted more in scale-out fabrics. And from our discussions, even with Madhu, I think we felt that that could be an area where we could make a difference with Gen Z, I think, in terms of it being the fabric which could be used. And the reason Gen Z becomes a key interconnect there is some of these features. It has huge network addressing capability. So you have a component ID space which goes up to 2 power 28. So you can have 268 million components on the fabric. And this is one of the areas where HPE is initially looking at in terms of creating exascale solutions with Gen Z. And all this whole fabric is, like I said, it's a memory semantic fabric. So you could basically talk to anything like as if you're just doing reads or writes to it. And it makes it very simple. The second aspect is a scale-out fabric would need some messaging solution. And Gen Z provides that. So you can have things like MPI and OpenSHMEM and other technologies built on top of Gen Z and the libfabric implementation which is there to be able to take the packets over that. It provides a lot of redundancy and multipathing with things like virtual channels. So we have 32 virtual channels support with Gen Z. And you can segregate the traffic classes, so you can decide which traffic class is important and give it the higher priority. So a lot of such reliability features are built into the protocol. We talked about traffic classes. I think, again, like I said, you could have a latency-sensitive application, so you could have Gen Z use a different virtual channel for that versus the other traffic, which is maybe not so bandwidth sensitive. You have multiple plane support, so all this can be co-packaged within a single switch. So you can have packets which are going out all over the fabric and through a single switch and get the same level of reliability. It supports a lot of the protocols which things like Omnipath and InfiniBand support in terms of adaptive and dispersive routing. And so it's pretty good as an interconnect for a scale-out fabric. And finally, it's low latency forward error correction, so it's just 2 nanoseconds per link hop. So now we come to the meat of the presentation. We'll talk about what RISC-V can do for Gen Z to take advantage of Gen Z. So one of the things, like I said in the earlier slide when I showed the bandwidth figures, is that if you have like 400 gigabytes per second of DDR and then just replace some of the PCIe with PCIe lanes with Gen Z, and Gen Z is compatible with the physical layer of PCIe, so you could just have Gen Z lanes coming out there instead of PCIe. So if you just do that, if you support Gen Z in addition to DDR natively, you can differentiate from processors supporting only DDR natively. And with RISC-V being a new processor, with no baggage of some of the other processors, it makes it easier to adopt an open fabric solution from that perspective. The second part is around physical addressing. So RISC-V has, one of the advantages with RISC-V is the larger physical addressing which we are seeing there. You see the x86 side and all, it's been very hard to get them to increase their physical addressing. You'll probably see that happening only in the 2019 or 2020 timeframe there. But we already see solutions with RISC-V supporting 52 or even 56-bit physical addressing. I think there's a lot of flexibility there. And so we would like to see a large physical address space because, like I said, all memory would be accessible to the system now. So it could be a fabric of fabric-attached memory, and so you could have just an SoC being able to access memory all over the place. And that would mean if you have a higher physical addressing, then it makes it easier to support that kind of fabric. The third point is around cache management challenges. I think RISC-V has traditionally been a bit wary of making changes with respect to caches, with respect to prefetching and things like that. But this is an area to, again, probably work with Gen Z together and make sure that some of the cache flushes and the prefetching and other things are implemented right so that things could be coherent in the Gen Z fabric, which itself doesn't give you coherency. The fourth point, like I said, if it can support a minimum of 64 Gen Z lanes of the PCIe 5 today, you could easily go up to 400 gigabytes per second for both DDR and Gen Z on the system and could take you to 800 gigabytes per second, which is pretty huge. A point around SCM, I think SCM will mean that you will have to have, you'll have longer latencies to SCM. So, but you might have to have a lot more transactions to be able to maintain the bandwidth which is there. So you will have to have outstanding transactions increased on the coherency interface, whether it's AXI4 or TileLink or whichever one is the one being supported. Memory mapping, I think we'll talk a bit more about this. Gen Z has the concept of a ZMMU, which does the memory, which is the memory mapped unit and does the memory translation. So we'll talk a bit more about that in the coming slides. We'll talk a bit more about LPD support for PCIe compatibility also in the coming slides. a similar point to the cache management challenges which I talked about is the implementation of FAR atomics. If Gen Z can implement FAR atomics like what ARM version 8.2 is thinking of now, it would help because you can actually transport the atomics over the Gen Z fabric to the actual device, and the atomics could happen there. And that makes sense, again, like I said, in a fabric-attached memory environment. I talked about Gen Z security features. Again, I have a slide on that. I'll talk a bit more about that. And finally, I think there's a lot of opportunities with the protection translation architecture for a secure fabric. I think RISC-V is, again, rethinking the way protection and translation should be done. It's not all based on the MMU. I think we've been thinking of capabilities and other things. I think these are opportunities because Gen Z also provides a level of protection which can be reused, and then you could have the translation happening along with the Gen Z MMU. So at a high level on the ZMMU, so like I said, Gen Z has a MMU which there's both a requester MMU and a responder MMU. The requester MMU will be on the SOC side, which would actually translate from the physical address on the MMUs on the SOC side to the Gen Z address on the fabric. And then on the device side, again, there will be another translation from the Gen Z address to the fabric address to the actual address on the device. And this ZMMU, there are multiple ways it can be implemented. It could be integrated into the system MMU, which is there on the RISC-V side, but that's usually very complex, and it also creates a linkage which may not be desirable. The other option is to probably go for a page grid-based MMU, which makes it simpler, ZMMU, which makes it simpler to be able to create the ZMMU on the requester side or on the CPU side. So that's one option which could be done. On the trust and security side, I think Gen Z has multiple things which are there which provide for security. The first one is access keys, which allow you to decide which component is accessible by which component. So whether an SOC can send packets to a particular component can be decided through access keys. You have R keys or region keys, where you can even say that this particular memory region on a particular device is accessible only to these components. So it provides you fine-grained control there. And this is where you could mix it with some of the capability protection on the SOC side. The other thing is you have whitelisting, where you can decide that these set of components can access this or be able to discover things on the fabric. You have a deeper packet authentication with things like anti-replay tags, which allows you to prevent a man-in-the-middle kind of attacks. So you see that, in fact, on the right-hand side, you have these components A and C on the fabric configured with a green transaction integrity key, and then the packet is encrypted along with that and sent off to the other side. And the remote side is also configured with the same TIK, and so it knows how to decrypt and then figure out if it's the right packet. It also maintains sequences, which allows you to decide whether there's a man in the middle who's doing a replay or not. So there's a high degree of security which is there in the Gen Z fabric, and again, like I said, RISC-V could add capabilities like the capability support on the SOC side. You could also do something like a trust zone capability, which allows you to configure memory on the fabric to be accessible only by certain components. So that's one option. So there are lots of options which can be done to improve the security. Like I said, on Gen Z will not be there from, you will not have Gen Z support from all operating systems, for instance, from the beginning. So you will need to have compatibility, and that's where the spec allows you to be able to discover Gen Z devices through what is called a logical PCI device mechanism. And what this means is that on the platform side, you have to implement what is known as a PCIe enhanced ECAM, or an enhanced configuration access mechanism. And that will allow you to be able to address PCIe as memory mapped, the configuration space, and which will allow you to even discover Gen Z devices. LPDs can fully exploit the Gen Z architecture. There are features which you would get with a native Gen Z implementation, but I think most of it is covered through LPD. And switching with Gen Z is pretty low latency. It's just 30 nanoseconds versus PCIe, which is 130 to 150 nanoseconds, because it enforces ordering or on the PCIe side, while Gen Z doesn't have ordering limitations. So this is, for a round trip, this translates to a huge savings of around 200 to 240 nanoseconds. Like I said, I was having the suggestion around RISC-V atomics. I think today all atomics are supported with Gen Z, and I think if RISC-V comes up with a version of FAR atomics, I think it would really work well with the Gen Z architecture. There are a lot more points here. I think I don't have to stress on any of those, but you have things which I talked about, like multipath aggregation, resiliency, and then you have the PCIe physical links which are supported with Gen Z too. So you have support for both the PCIe as well as the electric 802.3 specification which is supported. So just a slide on the application performance side. So what Gen Z can do to the application performance. I think, like I said, it allows you to have a fabric attached memory, which allows you to be able to have all your application data in memory. And that can really completely transform the way applications have been working today when they either go to storage or something like that to do something. They have to bring the working set into memory and then work on it. If they could have full access to the memory or the storage, even through a load store kind of semantic, then that really transforms applications. And we have seen some of that with the machine kind of prototypes in HPE, where we have seen it with Spark with like 15x performance improvement. With some of the large-scale graph inference, we've seen 100x. And we have seen even more with some of the others where we can keep the financial models where we can keep the whole thing in memory. So we've even seen 8,000x in some cases. So it can really transform applications. So if you can move to a Gen Z-based fabric-attached memory. A slide on the consortium. It's already up to more than 55 plus members. I think we have components. We have CPU vendors like ARM and AMD there. We have GPU folks and storage class memory. I think people are already developing memory modules based on Gen Z, and HP has been developing the bridge side IP and the switches and things like that. So there is a lot of work which is already going on, and you will see some of that in the Flash Storage Summit this year, where there will be demos around it. It would also be good if RISC-V could be part of the consortium. I know there have been discussions around that, and maybe that's something to look for in the future. These are some of the milestones. I won't really talk through them. I think the version 1.0 of the spec is already out, and there is a lot more work happening, especially on the security side with encryption, page-level encryption, and things like that. The physical layer is also going through a lot of enhancements, and so you will see some of that coming out this year. And so I think the time is ripe for RISC-V and Gen Z to work together and make sure that we have systems which are open all the way from the processors to the fabric. This slide is basically just a high-level slide which shows you how you could have RISC-V working with Gen Z. So you could have an SoC where you could have a Gen Z logic within the CPU, and then talking to the SCMs. It could be attached to GPUs or FPGAs. You could have switches out there which allows you to talk to multiple modules, GPUs, FPGAs, and things like that. So it really, like I said, from the motherboard to the rack to the fabric, I think it opens up a huge area of opportunities without any protocol translations, which are typically there now with multiple protocols which are there. So it's a futuristic area, but it's an area to think about. I think it would solve a lot of problems, and I look forward to working on RISC-V along with to make Gen Z the protocol of the future.
So it looks like a great combination of what used to be something called FBDIMM, which is actually isolating the type of memory technology with respect to the connectivity to a CPU on one side, and on the other side, omnipath or InfiniBand kind of connections that are there,
right,
which is actually connecting between systems. Definitely, I think it's a good technology. And in terms of adoption, I think time will tell whether the new other technologies coming up in the form of, like, say, UPI and things like that, how it challenges with this.
Right.
But my question is actually, in the current form, what RISC-V is, having the kind of capabilities of Gen Z that I saw in terms of performance, bandwidth, and all that, is that ready for a RISC-V kind of a SoC talking to a Gen Z?
I think that's a difficult question for me to answer, but I think what I feel is that RISC-V has advantages over other processors in terms of, like I said, it doesn't have the baggage which other processors have. So if you have to develop a native implementation, it's probably more easy because people are only starting now to develop some of the RISC-V based systems. I think that's where there is an opportunity where RISC-V could actually start working on this, the links sooner than other vendors, and then get solutions out faster with Gen Z. But in terms of actual products and where you can use it, I think that the use cases need to be thought about a bit more. I think, like I said, we've talked with Madhu around the possibility of rack scale solutions with HPC scale out fabrics. Maybe that's where it'll start, because RISC-V, you will not probably get those large servers or something like that, but you could get smaller accelerators which you could attach to the Gen Z fabric and get good performance.
Okay, so since you're talking about like a heterogeneous environment, and Gen Z has, if it is a Gen Z fabric, how is this discovery and management of the fabric has been controlled?
Yeah, so Gen Z defines the whole management specification too. So you can have fabric management which is there. It's kind of similar to the way InfiniBand did it with the subnet management. I think you will have a fabric manager which is going to discover the fabric, configure the fabric and things like that. And a lot of that is being worked out right now.
Okay, so the spec is having that info today?
Yes, it has some of that input, but the overall fabric management specification as a separate one is being developed.
Okay, so Intel Rascal design is also a contributor to this consortium?
Intel is not part of this consortium right now. I think they have been, people have talked to them about it. I think right now probably it doesn't match with their product plans with things like Omnipath and their work with Altera and other things. But yeah, maybe it's a possibility in the future.
In your presentation, you mentioned that it's basically out of order scheduling.
Yeah.
Like PCI Express, the order is not maintained.
Yeah.
So then how memory coherency is granted or
yeah,
guaranteed?
so coherency is not really part of the base Gen Z spec. Okay. So that's where I think Gen Z would, for the coherency protocol, you would probably have a different coherency protocol. So you could have something else there which kind of bridges to Gen Z and goes over Gen Z outside the box. So Gen Z itself doesn't prescribe coherency, especially in the fabric. And that is where I think, like I said, if you have things like this far atomics, which you could actually use to do the coherency part, I think you could, the applications will have to basically handle that coherency. Because when you go to really huge memory and huge systems accessing that memory, it's almost physically impossible to have hardware coherency. So you will have to do it at some software levels only.
You've seen how effective the collaboration on RISC-V is, and how many open implementations and Libre licensed implementations there are. Is there a open Gen Z Libre licensed controller available?
Sorry, is
there a Libre licensed open Gen Z controller available that I can download now and actually put into an FPGA without signing an NDA and et cetera, et cetera?
That's a good question. I think there were similar questions from Madhu also. I think that's something which you can probably work with the consortium. I think the consortium is giving out some of those IPs, and I think if you join, but you have to join the consortium first.
Yeah.
So
okay. So what's the that you join the consortium, which means that I'm required to restrict what I can and cannot do, think, or say.
Hang on, I can probably add to that. We had the same question. No. See, we are part of the Rapid.io consortium, and we are developing, and we have an open source controller. That's not fully done. It's kind of coming along.
Good.
It's a BSD licensed one. We were also planning to do an open source BSD licensed Gen Z controller. The Gen Z consortium did not have any objection to it. The standard is also open. You can just go into the net, download it. You don't have to join. And in Gen Z, if you're an academic or a non-profit, the membership is free.
Yeah.
You don't have to pay for it. They don't seem to have any philosophical objections to a Libre controller. That's the best I can say. So nothing that prevents anybody from doing it. On the contrary, I think they want to encourage that.
Great. So now I'm interested because I would want to actually put that into a chip.
Okay.
Yeah, thank you.
Thanks.
What you might want to try is actually use the USB 3.2 3.1's alt lanes to run Gen Z.